Have you ever seen a beautiful picture of space, perhaps of a nebula or a galaxy, and wondered if the colors are real or how big it appears in the sky? Many pictures of the cosmos seem abstract and removed from our daily experience. The irony is that pictures of space capture that which is most common and ubiquitous. It is our daily life on Earth that affords us a uniquely special view. You see, the problem is, when looking at astrophotography, there are no people or easily identifiable references to orient oneself. Yes, the abstract form of a nebula can be beautiful without any further consideration. But if you saw a picture of a person that was green, or they stood taller than a house, you would instantly reassess the information that picture communicates. There's a similar skill set that can be applied to astrophotographs, and that is what I'd like to show you in this presentation. With that in mind, join me on a journey through space and time and revel in the mystery of the universe. We live in a world of images, and our digital lives rely on our ability to interpret them. It is a skill honed by countless hours in front of screens, big and small. However, some kinds of images, especially those that depict tremendous scales of size or time, defy our ability to easily interpret them. So the images that you'll see through this presentation are ones that I've taken, unless they are, otherwise noted. So these images were not chosen randomly. They exhibit what inspires the most commonly asked question: what are the sparkles or lines emanating from the stars? Some people think that they're put there for artistic reasons. Others don't question their appearance in photographs because it meets an expectation of what a star should look like based on drawings or cartoons. These patterns are indeed artifacts produced by certain telescope designs. Reflecting telescopes that use mirrors have structures that hold secondary mirrors or other instruments. These rods or vanes obstruct small amounts of light that enter the telescope, and through a process called diffraction, the light rays are scattered. These so-called diffraction spikes are not desirable, and some form of diffraction will always occur for any obstruction. The images shown so far were produced with this particular telescope, the Schulman telescope. It is the primary telescope at the University of Arizona Mount Lemmon SkyCenter. This telescope is available to take images with, just like the ones you've seen so far. You can see the vanes that support the secondary mirror here at the top of the telescope. Notice how in this image, produced with a telescope that uses only lenses, there are no diffraction patterns. There are no obstructions to cause it. Most large telescopes use mirrors because it's not advantageous or even possible to build telescopes made only of glass lenses. This is why most professional images have diffraction patterns. On a more philosophical note, notice how the light of stars is spread into its spectrum of colors. The diffraction of light into its component wavelengths is a primary way most astronomical measurements are made. Even though these are artifacts, the fundamental information is literally encoded in these images. It's as if the universe wants us to discover the answers if we only look hard enough and ask the right questions. Scintillating diffraction patterns are only but a superficial element of astronomical images. There are much deeper considerations of what is recorded in an image. Typical CCD cameras that are optimized for astrophotography are very sensitive and can record many tens of thousands of discrete brightness levels. Computer monitors, by comparison, only display 255 grayscales. An astrophotographer then must choose how to represent and render the data recorded in an image. This is a picture of a wonderful spiral galaxy, and although its splendor is recorded in the data, those values are being rendered in its unstretched form with a monitor only displaying the first few hundred brightness levels. By changing the white and black points, more of the data can be visualized. Now we see a galaxy in the center with some spiral structure, as well as a few other galaxies in the background. Finally, by representing the data in a nonlinear way, the faintest values displayed are proportionally brighter than the other elements of the image where they were already bright. However, even more of the story is revealed. Now we can see faint spiral arms as well as the tidal tails of other interacting galaxies. When looking at an astrophotograph, keep in mind that the person who creates the image consciously decides this element of representation, as well as many others, as we'll see. Blend in the color information. This is where my slide, yeah, there we go. Blend in the color information, and now you can see that it takes on new dimensions. Notice how I chose the display of the faintest and noisiest features as just delicately hinted. This communicates that those features are truly difficult to see relative to the other elements. The colors represented in astrophotography come in a few major variations. The images you've seen so far are all in the visible wavelengths of light. However, this is only a very small fraction of the electromagnetic spectrum, and astronomers pursue the entire span of energies that can be detected with instrumentation. With regards to the light that we perceive with our eyes, even if looking through the largest telescopes in the world, the universe would not appear with the vibrant colors shown in these images. Our biology is simply not designed to detect these minuscule quantities of light. A full color image of visible light is created with a camera that filters or discriminates between reddish light, greenish light, and bluish light. These pictures are called broadband images, and when the images are assembled, the colors of light are mixed together in a way that is analogous to what our brains do. So in a picture like this, I do not choose that this should be blue or that this part be red. If your eyes were as sensitive as the camera that was used and you could expose for as long, this is approximately what you would see. Sometimes people ask if an image such as this is enhanced in terms of color. I take a different perspective. I explain that it is our view of the universe with eyeballs which is diminished. If you look through any telescope in the world at this object, you would not see any color in this nebula. Yet red and blue wavelengths of light would truly be hitting your eye. In this sense, then, this picture isn't an enhancement, but a more accurate portrayal of reality. And these instruments become our surrogate senses that allow us to understand the world around us. Another kind of color representation is done through what is called narrowband imagery. This method captures light of specific wavelengths, which results in a high contrast image of nebular features. However, this isn't a true full color image because all of the other wavelengths of light are not included. Here is a broadband image of the Eagle Nebula with the very famous pillars of creation in the center. These pillars were made famous by the iconic Hubble Space Telescope picture of them. The HST picture is a narrowband image. Note the wavelengths used here were one green portion and two red parts. These were then mapped as red, green, and blue, resulting in a mapped narrowband image, which is an arbitrary color assignment. As you can see, the HST picture of the Eagle Nebula is a small portion of a much larger object. This leads us to an important idea concerning resolution and field of view. When looking at an astrophotograph, each pixel of a sensor detects light from a very small patch of sky. The size of this area on the sky determines the finest possible resolution of an image. For a quick review of angular dimensions, a degree, perhaps the size of your fingertip held at arm's length, can be divided into 60 arc minutes. The moon subtends 1/2 a degree on the sky, so it's approximately 30 arc minutes across. A crater on the moon might be several arc minutes in size. An arc minute can again be divided into 60 arc seconds. So a bump on a crater on the moon might be of this size. Taken together, the array of pixels determines the full field of view. The HST picture of the pillars is only a few arc minutes in dimension, whereas the field of view from the picture of the Schulman telescope is 10 times larger, though this is still smaller than the diameter of the moon itself. However, there's something deceptive at play here. Each pixel of the HST image sees a tiny 0.05 squares of the sky, arc-second squares of the sky, whereas a pixel in my image covers a patch of sky 6 times larger. Oops. Before I show a one-to-one comparison, there are some important rules of thumb to know about optical astronomy. First, stars are so far away that they're not resolved and they're truly points of light. However, as light passes through our atmosphere, the rays are deviated by small amounts. We live in an ocean of air, and our view of space from the ground is blurry. Typically, this blurriness smears images by 1 to 2 arc seconds. But with this, we now know enough information to start interpreting images of all sorts. Let's begin with this wide field image of the region of sky near the Orion Nebula. So the Orion Nebula is the portion, the brightest part there in the upper right. The image was acquired with this particular astrograph. Each pixel at the back of this telescope sees 5 arc seconds of the sky. Recall that stars are points and the atmosphere blurs images by 2 arc seconds, which is smaller than 5. This means that the stars in this image look a little pixelated, like little squares. The special name for this situation is called being undersampled. Now what we're going to do is overlay the region of sky captured by the Schulman telescope of the Orion Nebula and zoom in. Due to the increased scale, we can clearly see more details, and the stars are now blurred across many pixels. Finally, what we can do is overlay the HST picture and see things at their intrinsic resolution. The stars are nearly pixel-like and undersampled again. The fine details here are due more to the fact that the telescope is above the Earth's blurring atmosphere than it is due to the optics of HST. Did you notice that the HST picture is not a full-color image? One giveaway is that most nebula that have glowing clouds of hydrogen gas are pink or red. Other variations with multiple pastel hues are a good sign that the image is composed of mapped colors. Another thing to consider is that we now have 2 images with stars that are undersampled, both the wide field image and the HST image. So how in general can you tell the difference? The easiest way to know is to look at the size of the features in each object. If they are large compared to the field of view, it is more likely that it's a larger, maybe space-based telescope image. Wide field of view images will have small stars, but also small details. Finally, no matter what kind of astrophotograph you're looking at, the stars in the images will appear to vary in their size. Stars are points, but all telescopes, even space-based ones, create images in which the light is spread out due to diffraction. The brighter the star, the more of the scattered starlight you see. So sizes of stars in a given image only signify brightnesses, not true dimensions. Take, for example, this wide-field deep image of Betelgeuse. The star actually...
For example, this wide-field deep image of Betelgeuse.
This star actually fits on 1 pixel in this sensor, but the bright glow of scattered light can be seen to spill across hundreds of pixels. So let's use our skills to identify a few different types of images. First, we'll start with what this might be kind of a tricky image. This is a broadband image of one of the most colorful regions of the sky. Basically, each nebula type is shown here. There is red emission from the glowing hydrogen gas near the star on the right and more of it in the lower left. The top of the frame is dominated with bluish scattered light from dust. This is called a reflection nebula. And then finally, dark clouds of dust obscure the view, except where they thin, and then they show golden light. This is literally the palette of a large majority of diffuse nebulae. Can you tell if this was taken with a large telescope yielding a high-resolution image, or is this instead a wide-field image with undersampled stars and lower-resolution details? If you said that this was a wide-field image, you got it right. This certainly is. This is a 4 by 8 degree region of the sky. So this is kind of that intermediate image that Babak was talking about. You can see this much sky with your eye. You could fit 64 moons in this field of view. Galaxies such as these are so far away that only our imaginations can span the distances. As such, when we look at galaxies, we are seeing great averages of information. The combined light of stars and nebulae in other galaxies lends itself to low contrast details and colors because many things appear mixed together. For this reason, it's unusual to see mapped color images of galaxies. Perhaps an exception would be when they are our nearest neighbors. Here's a broadband image of M82 with an enhancement in the hydrogen alpha emission that corresponds to the colors of the red filaments of gas being expelled from this starburst galaxy. The colors are the same without the enhancement, but adding more signal to this particular feature, the added contrast makes the image much more compelling. When mapped colors are employed, the result is obvious and can highlight structures of galaxies. Here, radio wavelengths of light mapped as blue trace cool molecular clouds of hydrogen gas and show the skeleton of the galaxy. Here's a broadband image of the same. Now, this is a full color image of what is effectively a narrowband object. This is a dying star that has lost its outer layers of gas. Our own sun may eventually end its life billions of years from now in a similar way. The sphere of gas fluoresces this characteristic blue-green color due to small amounts of oxygen in the nebula. This process always yields this color, which is why the HST picture of the same is an example of a mapped color image with its expected extraordinary detail. Here's another image. Is this a mapped color image? How about the resolution? What kind of telescope generated this data? Well, this is definitely a mapped color image, and note that the details are quite large. The difficulty is that many images are not posted at their intrinsic resolution. Even an HST picture like this can look like something a small telescope can accomplish from the ground, but when the full image is shown, the image characteristics become obvious. Finally, how about this one? This is another mapped color image, but this time it really is a wide field image taken with a small telescope. While the colors and resolution of an astrophotograph are generally image attributes that can be seen directly, many other aspects of the processing can take place that produce an image are not as obvious. Certain kinds of digital processing leave characteristic artifacts or telltale signs. However, the important idea is that the images of space, these kinds, are not snapshots. Raw data are typically dark, colorless, and sometimes just plain uninteresting. An astrophotograph, then, is the sum of hundreds of processing choices that are made to render the final image. Given the same data, different people will end up with different results. I'd like to highlight just a tiny few of these considerations to give a taste of what these decisions look like. When the initial data is initially displayed, it's possible to identify colors or details that are desirable to have be represented in the final image. Many processing choices will blunt the effort or make it an unattainable goal. Seeing the final image in your mind and processing the data in small methodical steps can help stay on course. In this image, each of these features were observed early on in the data and maintained with every subsequent step. CCD sensors produce linear data, and that data exceeds a monitor's ability to be able to display everything at once. And so nonlinear ways of displaying tonal variations are crucial. Without the use of high dynamic range algorithms, the interesting features of this galaxy could not be displayed. Note the inner disk with bluish tips and thin dust lanes, as well as the outer distortion in the galaxy's halo. In fact, these kinds of decisions are not unlike what Ansel Adams would make when he adjusted the tonal values of his images. What interested him was not what he saw in his camera, but instead what he pre-visualized in his mind as a final image. He would then dodge and burn his film to achieve his vision. With astrophotographs, typically these adjustments are applied globally, and if not, if done selectively, they are conditionally applied based on thresholds of brightness, color, or contrast. High contrast in particular is an image attribute that is preferred by image makers and image viewers alike. There is an ancient evolutionary preference for high contrast, and this preference is shared cross-culturally. Adams, of course, knew this and played with it in his photography. The same lessons apply to astrophotography, but with some caveats. Take this image of the Trifid Nebula. Which version do you find the most compelling? There's no right or wrong answer. These are just simply different choices. However, there are consequences for the choices that are made, and that is something to be appreciated. If you didn't guess, my image is the one on the left. Although I could cater to the sugar high that contrast gives, I don't, because it comes with a cost. Light that filters through the clouds of dust has subtle attenuations and depth which I feel are lost and flattened with the opaqueness that high contrast creates. To me, there exist truths in astrophysical objects, and I enjoy communicating as many as are captured in the data. For example, here are 3 images of the famous galaxy NGC 7331. This galaxy features wonderful dust lanes in its disk that reach all the way to the center. With particular processing choices, it's possible to display the dust lanes all the way to the core, clearly and distinctly. But to me, the cost is high. Galaxies are truly brighter in their centers compared to their outer disks. Maintaining this truth, and at the same time showing as many dust lanes as possible, that's my style. This means that although I show the dust lanes, they are more difficult to see in the center due to the lack of contrast, but to me that's exactly what I would expect when looking at something this bright. And I have another example where I've processed the galaxy. It's coming up here. Yeah, I processed this galaxy with this to show what high contrast looks like on the right, but I very much like the more natural appearance of the one on the left, even though you may not see the nth detail in every dust lane. So here is a picture of what appears to be a relatively nondescript picture of space. But one of the very best astrophotographs ever taken was of an object hidden in the inky blackness of this field of view. In fact, to appreciate just how superlative this image is, we're going to use some of the lessons we've learned so far in this video, as well as kind of find our place in the universe. To travel to the large distances that we need to, light speed is necessary. Light in a particular unit of time travels a particular distance. Take, for example, sunlight. It takes light from the sun 8 minutes once emitted from the sun to reach us here on the Earth. So we say that the sun is 8 light minutes away. Now, if we use this and perhaps all too terribly small Earth-like units to measure that distance, it turns out to be around 93 million miles. So Earth-like units are not very good units to measure distances in space. Instead, these units of light units are much more appropriate and convenient for measuring the distances in space. So take, for example, the size of our solar system. And I'm going to be generous here and include the interesting parts, just the interesting parts of our solar system. It might be around 1 light day across. It takes about a 24-hour period for light to go from one side to the other. What I'd like to do is create a model that allows us to appreciate how far away the nearest stars are and how large our galaxy is and where all of these other galaxies are. There were galaxies in that initial picture I showed you. So what I'd like to do is build a model from a penny. I'm going to use this penny to do so, and I'm going to squish our entire solar system into the penny. Oh, let's see, I'm squishing. Squish. I think I'm squishing. Oh, I'm not squishing yet. This is the problem. I got to pause and go. Oh, there it is. Now I've squished it. Okay. So, and that really is a lot of squishing. If you were to make our entire solar system somehow fit to within the size of a penny, that means that the sun, the earth, comets, asteroids, everything you know and love is now squished into this little penny area. A penny is a little bit more than perhaps a centimeter in size, but that makes the numbers kind of nice. So let's say that 1 centimeter is now the size of 1 light day. At this scale, then we can imagine how far away the very nearest star is. And of course, you'll know the very nearest star is Alpha Centauri, and it's located 4 light years away. At this scale, 1 light day is 1 centimeter, one of those, let's make sure that's here. Yeah, one of those pennies. So a light year is going to be 365 centimeters, or a little bit more than 3 meters away. Alpha Centauri at this scale then is 4 times further. So 4 times 3 meters is 12 meters away. Now, imagine you want to describe the size of our galaxy. You only need to know basically 2 numbers. You just need to know how many stars are in our galaxy, and this would be how many pennies I would need to build a penny galaxy to complete our model. And I also need to, I need to know how large the galaxy is. So you need to know how many stars and how large the galaxy is in extent. So I think I have a nice picture here of, a galaxy. Well, our galaxy contains on the order of 200 billion stars, and it's no less than 100,000 light years across. So to build our penny galaxy, I need to begin with 200 billion pennies. If I had 200 billion pennies, I'd be a pretty happy guy. Unfortunately, there aren't that many coins in circulation in the US, but this is, of course, in our imagination. I would need to spread the pennies out by some average distance from one another to build this galaxy. So let's say that from star to star in our galaxy, our nearest neighbor is 4 light years away, but let's just say the average distance from star to star might be 2 light years from one another. So 2 light years, of course, is going to be 6 meters, because that's 2 times the 3 meters. So it's about 20 feet or so away. That's how many feet from penny to penny I'd need to spread these things out. And if I actually did this, it would take a long time. If I tried to spread pennies out 20 feet by one another and did this for all 200 billion pennies, even with 1,000 people setting down 1 penny every few seconds nonstop, it would still take about a decade to complete this project. But again, keep in mind, this is just all within our imagination, right? In this model, if 1 light year is around 3 meters, then the galaxy is going to be 300,000 meters across, because the galaxy is 100,000 light years across. So that's 300 kilometers. And the numbers I've been using are actually too small, because a penny is bigger than 1 centimeter. And it's not 3 meters, but it's 3.6 meters. So the galaxy is actually larger if you make it a 1 light day, but I'm just trying to keep the numbers really easy here. Just imagine then, if this becomes the size of our galaxy, if you make our solar system or a light day just the penny, then even the nearest neighbors of other galaxies, the Earth isn't large enough to contain this model, and we end up having to display other galaxies off of the Earth. So our nearest galactic neighbor is the Andromeda Galaxy at 2.5 million light years away. So this is the scale that I wanted to set up. The Andromeda Galaxy in this image spans more than 4 degrees of the sky. If you were over there looking back at us, this is how we might appear. Though I'd like to think that we have, better spiral arms. The stars you see in this picture are all in the foreground and part of our own galaxy. Zooming into the center reveals dust lanes that swirl all the way into the nucleus. Note that I was not too aggressive with the contrast in order to communicate the brilliance of the downtown galactic center. So we live on the outskirts of what is the Virgo cluster of galaxies, the center of which is around 40 million light years away, and that is what this is a picture of. So this is a wide field image of that part of the sky that contains thousands of galaxies. Though they're hard to see at this scale, you can see some of them as little fuzzy oval blobs here. If you look in the, I hope my cursor is showing up here. If you look in the bottom right, you can see a number of them, and then you'd really need to put on your magnifying glass or something to find some of the others that are scattered throughout this field of view. So I'm going to need to do a trick here. I need to go ahead because of the way that I did this. So I need to go to trying. Yeah, so you're not supposed to see that. What I want to show you is a labeled view of this area. This is an annotated view, which labels every single galaxy in the field. And what I'd like you to note is how there is a gradient of galaxies that go from the top left to the bottom right. So it should be obvious just based on the labels where the direction towards the center of the Virgo cluster of galaxies is. So now I'm going to go back to where that was. Here. Oh. Here. Because what I want to point out are some of these galaxies in particular. I've been fortunate enough to have, had opportunities to take pictures of many of these galaxies. And it's always nice, just as Babak showed, to see both what they look like at a wide kind of field angle and then zoom in to see them at higher resolution with perhaps bigger telescopes, longer focal length instrumentation. So the circular patch right here, that is the wonderful, one of the largest spiral galaxies in the Virgo cluster, M100. Really beautiful galaxy. When you display it, of course, in full resolution, you see all of the wonderful details. Another example is a kind of a binary set of galaxies here, where they show 2 different types, where we have an elliptical and a spiral. Those are located right down here near the bottom. They look like 2 little fuzzy blobs. And one of my favorite galaxies, also in that same area here, is M58. And I think it's an overlooked galaxy that people should really pay attention to. I just think it's a fantastic galaxy, really. And then finally, 2 very spectacular spirals are here, where we have M91 and M88. But what I'd like to do next, I'm going to go back, or actually I'll go forward here, is journey to what is perhaps the most remarkable galaxy in the Virgo cluster. And it's this oval patch right here. This is M87. And it is the location of where the best astrophotograph, I think, has been taken, and that really is where we're going to go. So.
Long.
Oh, can you still hear me, guys? Let's be sure I'm still on.
Yep.
Here we journey to the heart of the Virgo cluster, to M87. And this galaxy certainly is the result of collisions of many galaxies. M87 has the mass of not billions, but trillions of stars. Magnifying the view more from the Pommenus astrograph to the Schulman telescope shows that there is something remarkable coming out of the core. It's unlike anything else observed in the local universe. This is a relativistic jet of gas and energy that stretches for tens of thousands of light years. Zooming in more with the HST image shows the detail in the jet and hints at the fact that there is something monstrous, something very powerful in the core of M87 to create this outflow. The only thing known in the universe that can generate this much energy is a black hole, and that is what has been assumed, but nary a single example ever directly seen until now. If you recall, each pixel of HST sees a tiny 0.05 arc seconds of the sky. If we zoom in to just a single pixel in this image, right in the center, and make it fill 1,000 pixels on the screen, then the center pixel is the size of the region captured by the Event Horizon Telescope collaboration. This feat required combining light simultaneously captured from a network of telescopes that spanned the globe. Nothing less than a telescope effectively the size of the Earth could have enough resolution to capture this region and directly observe the black hole at the heart of M87. This I would consider a mapped image, but it's a single wavelength of light. It's a false color image that is made from short radio wavelengths of light that were used to create this particular picture. So before the spring of 2017, pictures of black holes and magical unicorns were in the same category. We live in a time when a century-old question, one for which much ink has been spilled, is answered. Yes, there are black holes in the universe, and yes, much of the physics looks about right. The region shown here is roughly a light day in extent, recalled a penny, and has a mass of around 6 billion suns. This image is as fantastic as the object it captures. It's a first of a kind, it's a one of a kind, and it really is an unbelievable astrophotograph to behold. So I wanted to highlight that particular image in general because I feel that only by going through my presentation that I just gave, with an understanding of everything from wavelengths to how you display the images to the size of the resolution of what you're seeing on the sky, even though that's kind of like a fuzzy image, only with all that information taken in context can you really appreciate what was done there. And with that, I'm going to say that that's going to be my presentation for a way to interpret astronomical images with a particular example in mind, that particular EHT image.
Excellent.